one talk left this session. Lailai Zhu from National University of Singapore, telling us about emerging states of Phoretic active matter, and we have about a minute before he starts. Maybe you get started.
Okay, thank you. Thank you. So I'm Lailai, I'm from National University of Singapore, and this work was done with my student, PhD student Qianhong, and former postdoc Maoqiang, and our collaborator Francesco. And today I'm going to talk about active matter that compose of so-called active droplets that have been realized in the lab in the last decade. So in principle, it is like a water droplet. You put it into an oil surfactant phase, and it just swims spontaneously without a field, a magnetic field or electrical field. So, and then as you can see, it does not really like the microorganism with a head-tail asymmetry like polarity, or the Janus particle with the intrinsic pre-designed coated, half-coated asymmetry. It does not, right? Even when it swims, right, there's high surface tension, it remains spherical symmetry. So the idea is that what breaks this like full asymmetry allow it to swim. So in a nutshell, it's induced by a hydrochemical like instability. So which I try to explain with this simple picture. So this red dot indicates these chemicals in the solvent. In this case, it might be miso that will change the surface tension along the droplets, along the surface of the droplet, leading to some potential Marconi flow. Okay. So initially, these red dots are homogeneously distributed, and then if we imagine an infinite small like disturbance in the chemical field, the red dot. So now they are diluted region and a concentrated region. Okay, so there will be the Marconi flow that's driven along the gradient or in the opposite direction of the gradient, namely either it's from the diluted region to the concentrated region or reversely. So in this particular picture, let's say, okay, this flow, Marconi flow, slip flow is just generated from diluted region to the concentrated region. Then this convective flow will further advance these chemicals from the diluted region to the concentrated region. Then this kind of amplifies this asymmetry in the disturbance of the chemical concentration, and then forming this positive feedback. This instability occurs, then the droplet swims. So this very simple physical picture has been theoretically characterized or modeled by Sebastian Michelin and Eric Lauger and Des Barthelot like in 2013. So the simple picture is that the droplet can be regarded as a spherical particle without internal flow, and then on the surface of the droplet, on the surface of the particle, it encodes a uniform solute releasing with a constant uniform and constant releasing of a chemical, and the diffusion rate of the chemical is D, and now on the surface slip velocity, this U slip tells you the Marconi flow, where M is the mobility. So in order to allow instability to occur, this A and M multiplication has to be positive. So here there's only one dimensionless parameter, which is Peckel number, indicates the destabilizing convective effect over the stabilizing solute effect. Because if we think about if we have a very strong diffusion rate, then whatever we put in the perturbation, then everything is going to be smoothed out. Then the particle, the droplet will be, the concentration will be isotropic and it will not swim. It just becomes stationary. So this is shown in this particular picture for a 3D case. Now the critical Peckel number is 4. Below this value, stationary and isotropic. Above that value, then you will start to see full after symmetry in the chemical concentration as well as the flow field. It swims, so it develops its own polarity. Okay. So as you can see, is that in this particular case we have this convection, right? Peckel number indicates the convection strength of convection. In terms of mathematical sense, it indicates nonlinearity because it is the velocity convects the concentration. It is similar to the Reynolds number, which indicates the nonlinearity of the convection, where it is the velocity convects itself. Okay, and we know that when in the typical classical fluid mechanics world, when we increase the Reynolds number, then the nonlinearity increases, then the flow will become laminar to chaotic and turbulent small scale feature will occur. So similar for this particular picture, for this Peckel number, it also indicates the strength of nonlinearity. So which means that when at low nonlinearity, low Peckel number in the experiments, the trajectory of droplet will rather be smooth. And if we increase the Peckel number, the nonlinearity is higher, then you will get a meandering trajectory. And further, if you increase the Peckel number, you will see the smaller scale pictures in the trajectory. And the same picture has also been shown in the two-dimensional simulation for a simple Phoretic disk. And this is, in this case, as you can see, ultimately, when you increase packet number, then you will get a completely chaotic trajectory. So this is a story we know about this, we know about this Phoretic droplet, which has been read just within 1 decade, right? And in fact, there's a similar mechanism, the so-called camphor disk, that have been seen with a similar mechanism that have been seen more than 1 century ago. So the idea is that now you put like a circular disc-like shaped camphor, and you put it on a on a water interface, and then put there. At a certain point, it will also swim. And this has been, after a long time ago, in this case, the chemical is a camphor that is releasing along the air-liquid interface, and then it will also potentially trigger this gradient in the surface tension leading to the potential flow on top of this subsurface flow. So there are some similarities that also, in order to make the swim, we need to have full outer symmetry and physicochemical instability. So it's chemical driven. Another thing, a similarity is, in fact, is found by several Japanese groups. They found that it depends on the packet number. Either the swim can swim like a persistently, steady, or intermittently. This is same as experiments. So the only difference that in this case, it's a millimeter scale rather than a micrometer scale, and also it is strictly swimming along a plane. So as you can see, that now we are thinking about like the swimmer with the individual swimmer need to swim undergo instability. It can be chaotic. It's slightly different with like pattern formation for the classical like active fluid. It's a whole system become unstable. Now even one single swimmer can become swimmer because of instability. And now we are thinking about what if we have a lot of those swimmers, then they can interact with each other, including hydrodynamics, chemical, and so you have multiple routes and multiple swimmers. So we are thinking about whether this like a collective like a behavior would like promote or prohibit this kind of instability or chaos. This we don't know. This we try to answer. So we have some experiments, as you can see, is that in these experiments they mention this collective behavior but not address it. And also in the quite recent work, the group of Koreans, they try to understand the interaction between a pair of 2 droplets. Okay, so they are focusing on the trajectory of the pairs. So if we look at these camphor balls, we have something different, right? So in 2008, so what they found is that if you put a single swimmer, then it swims. But if you put many of them, around dozens of them, then they form this stationary lattice. Okay, it seems like, become stationary. On the other hand, if we look at the similar experiments, okay, also on camphor balls, now what you can see is you get this turbulence, common turbulence, then within around 30 disks. So we see there are some difference, and this is something we try to address in this work. So we try to do this with some numerical simulation, but from the wet active matter point of view, so we think of like 2-dimensional periodic box with many this kind of 2-dimensional disks, and here I use tilde to indicate the dimensional parameters. And in the end, we end up with the dimensionless equations with one is a Stokes equation and the other one is a classical advection diffusion equation. So the only nonlinearity, okay, here I should have put the packet numbers. The only nonlinearity here is the velocity advection of the concentration. So in principle, here there are 2-way coupling here. On one hand is that here the velocity advects the concentration. On the other hand, there's the velocity, the gradient of concentration will influence the velocity on the disk. So there's a 2-way coupling here. So on top of the classical problem, there's only 1-dimensional parameter. Now we have 2-dimensional parameter. One is the packet number, the other one is air refraction. Of course, we have to assume that the size of periodic box is large enough. It's a plane. Okay. Then, okay, now we come up with our journey. Then we say, okay, now I have 2 parameters. Sorry. And I just fix the parameters. Then I start with phi with air refraction and packet number is equal to 0.2. And then I run the simulation. The arrows indicates the velocity, instantaneous velocity of the particle, and the white bluish stuff indicates the concentration. Okay, at a certain point, I need to drag a little bit. Okay, sorry, I need to drag it. This is not a very good video. But at a certain point, what you will see is that, okay, it will become stationary, and then, okay, it forms this pattern. So what we see is that, okay, this is so-called the Wigner crystal in a sense that has been like a hypothesis inserted by Wigner for this electrons. So what he thinks that in this case, the feature is that the distance between every molecule should be much larger than the size of electron. It has been recently visualized experimentally. So in the original case for the Wigner crystal, it is created because of long-range electrostatic or the Coulomb repulsion between the electrons. But in our case, we don't have it, right? But in our case, we have a similar mechanism because our Phoretic disks are due to this, are subject to this long-range chemical repulsion, which leads to this kind of Wigner crystal. And on the other hand, we can see that at a certain point, qualitatively, it reproduces the equivalence. Okay. So now we have, phi is equal to 0.2 and the packet number equal to 2. Now we slightly increase packet number to 3. So what we see is something like this. So again, I need to drag or maybe let it play a little bit. As you can see, gradually it will form some patterns like the train formation and so on. But maybe I can let it play, but we can look at the radial distribution function. Soon we can see that somehow you have peak and then goes to 0. It looks like the typical radial distribution function of a gas phase. But on top of that, we have something else in a sense that we have seen the peaks that are developed at 2, 4, 6, 8. And these two, okay, here, this particle-particle radius is scaled by the radius. Particle-particle distance is scaled by the radius. So this kind of emergence of 2, 4, 6, 8 is because of the typical feature of the train formation, because this is the typical radial distribution. So as you can see, at a certain point, we also reproduce the formal experimental results about this train formation, especially this arc-shaped or train. Okay, so this is one thing. So naively, we might think that for the packet number 2, you get solid state, and the packet number 3, you get a gas phase. In principle, at the packet number 2, and in between, you might get some liquid phase. So this is what we are trying to do, and I'm trying to show you. So there's not too much to say is that it's not become stationary or like the train formation or the gas phase, but from the radial distribution function, we can easily see that it looks like that of a typical liquid phase. Okay, so now we see that this liquid phase has not been reported experimentally at all, and then when we look at the phase diagram, okay, so the horizontal axis is the phi, and this packet number is and this part is the gas phase, and in between this part is the solid phase, and in between is liquid phase. We can see that numerically we can easily tune the parameters such that we can get different phases. But experimentally, of course, it might be too expensive or impossible to really tune these parameters with ease. Okay, so this is what we get. Now I have to confess that this kind of phase diagram is obtained by embarrassingly expensive numerical simulation. So what we try to ask is that whether we might get some theoretical understanding about this picture. At least we say, okay, so in this part, this is stationary. So above that part, you get liquid phase, you get the collective remodeling, get liquid phase. So somehow I might borrow knowledge from, let's say, hydrodynamic stability to do some stability analysis or arguments to characterize this like melting behavior. So this is what we do. And we say, okay, now I'm going to do some stability analysis, but I'm going to starting just with scaling arguments. So what we do is that, okay, so we're starting from the dimensional equation, right? The tilde indicates dimensional, and this is so this is a convective term that is destabilizing, and this diffusion term is stabilizing. So I say I'm going to assume that the instability will occur when this destabilizing effect over the stabilizing effect is larger than a certain value, C, which I don't know. I put it here. Since I'm going to do scaling arguments, then I say I'm going to choose a characteristic velocity and a characteristic concentration gradient. These are just natural scales which I use to derive my dimensionless equations. There's nothing too much to say. Okay. The only thing I want to say is here in the denominator you have a gradient of gradient or the Laplacian C, right? So how do I get the characteristic scale of the gradient of gradient C? So in principle, then I realize, okay, now we look at the base state. If we look at the base state, everything is symmetric in the sense that you have a six-fold symmetry. So if I choose a point, let's say this cross between every two particles, then I realize it follows, the concentration field has mirror symmetry in both directions, about this axis and about the axis. Using this mirror symmetry, we can immediately identify that the gradient C at this cross point should be a vectorial zero. Okay, now I'm going to use the far field approach. By using the far field approach, I say, okay, so now the gradient C at this center can be approximated by the gradient C at the boundary. But I know the boundary, right? Because the boundary, this is my boundary condition. So using this, I know, okay, now the gradient C at the center is A divided by D, and change over this distance to 0. But this distance is just half the lattice, which I know if I know the phi, right? So I put everything in. Now everything becomes geometric. So D is 2 radius. 2 radius is the diameter, and I put everything in. You get an instability criterion Pecker's number multiplied by this thing is larger than a certain value C, which I don't know, but I can fit it, right? If I fit it, you will get this nice quadratic scaling, which keeps the trend reasonably well. Of course, it's not going to work well in this regime because it's a far-field approximation, and only works when the air reflection is small enough. Okay, so we look at this, and further we try to look at the melting behavior. I mean, we look at the static structural factor, and to show that this in fact follows the so-called KTH-NY theory, in a sense that in this case the Pecker's number resembles effective temperature. We can look at it from the static structural factor. Okay, then the key story is that the scaling can follow the KTH-NY theory, as well as the population of the topological defects, how we can find the bounded dislocations in the solid phase and the fluid dislocations in the hexagonal phase, and the coexistence of the dislocations and the disclinations in the liquid phase. Okay, so something worth to mention is that although several previous active matter research all finds that their melting scenario follows the KTH-NY theory, the very recent work published in PIL mentions that they found that something very different is that densely packed ABB crystals, it can sustain very large deformation, and hence the decaying rate of this translational autocorrelation function can be much larger than the original prediction 1/3. Okay, so come to here. I'm trying to convince you that okay, in this case, we are sorry. The Pecker's number resembles the temperature which induces this activity induce a phase transition, right? So now I'm going to change the gear back. Initially, I start with Stokes equation for the solvent, and we end up with melting KTH-NY theory. Now I'm going to turn the gear back to hydrodynamics and fluid mechanics, because we realize that once the active melts, it becomes liquid, whether in the gas phase or in the liquid phase. And what we try to think is whether the immersion flows of this active fluid can resemble those of the classic fluid dynamics motion. Okay, so now we just focus on this densely populated region when air refraction is 0.5. So what we show is now is the average value, in a sense that with E is like I call it O'Reilly velocity, or you can regard it as like at every specific point we can get the disk average velocity or the macroscopic velocity. So what we can see is that when the Pecker's number is small enough, it is still liquid melt, but this like macroscopic velocity is negligible. But if you increase the Pecker's number from 3 to 5, now you get oscillatory flow. In a sense that when the Pecker's number is equal to 3, we can regard it as an active liquid at stationary, macroscopic stationary, though the disk is still moving. But for the Pecker's, now we look at what does this Pecker's number oscillatory flow mean somehow. I play for a while, but we can see that so it looks like a standing wave, so the particle goes to the corner and then comes back. This can be further demonstrated by the chymograph, which shows you the regular wave pattern. And more surprisingly, if we look at the time evolution of some signal, for example, in this case, the average, the macroscopic like air refraction, you can see it grows like a small value, and then it looks, and then nonlinear effect kicks in and saturates. So it.
Could you show the movie again?
Okay, sorry.
Thank you. Thank you.
Okay, sorry. So the interesting thing is that this picture, this like signal, looks as if we are thinking about a flow past a cylinder, and then when the Reynolds number is above certain value 48, then you will get this like through a linear mechanism, exponential growth, and then saturate, and then go to a steady state by a so-called Hopf bifurcation. So this is the idea. So now we say, okay, now Pecker's number is 5 to become unstable, maybe approach the onset of instability. Now we are just increase the Pecker's number from 5 to 10. What we will get is that this 5 to 10, it seems that this regular wave pattern get break down, and this is we call the wave pattern breakdown, and it manifests itself. This is macroscopic, right? It's a wave pattern breakdown. But the microscopic point of view, it manifests itself is that the coexistence of the wave, but also sometimes the occurrence of the clustering. So this clustering, of course, breaks the wave down, And on the other hand, we can also think about this clustering indicates the fluctuation of the effective active pressure. So somewhere there's the pressure fluctuation in time and space. And this kind of pressure fluctuation as well as the wave pattern breakdown is another like scenario of the transitional scenario in classical fluid dynamics. Now the Prandtl number is to 10, we get transitions. There's no surprise that if I further increase Prandtl number, I'm going to see the active turbulence. So this manifests in the coexistence of vortic structures as well as in the clusters. So this besides this like a visual sort of like demonstration, we can also look at this partial PDF of this longitudinal velocity difference. What we can see is that some like at a certain point we will get like fat-tailed PDF in a sense that this kind of region indicates some high amplitude extreme events associated to some intermittent process, which has been collectively known in this classical turbulence in the early 90s. And regarding this energy spectrum, there's not too much I can say in a sense that nowadays we might understand that this exponent might dependent on active matter systems. Okay, so now we come back to the experiments, right? So we know that our diagram shows something, but how is it related to the experiments? So we show that, okay, in this case, it is cell organized stationary, and in this case, it becomes turbulence. But how is it related? So we check very carefully about the two experimental papers. So we find that they use the same fabrication method because they cite each other, right? Or at least the later one cites the previous one. And then they have the same disk height, 500 to 600 microns. So the height is similar. So the only difference is actually the disk radius. What you can see is that on the left-hand side, so this is exactly their value, right? So on the left hand, this is 0.5 millimeter. On the right hand, 2.5. So if we look at the relationship between the Prandtl number and the A, you see it's linear related. So I can say that on the right-hand side, the Prandtl number is 5 times that of my left-hand side. So it means that, okay, the low Prandtl number, you get a crystalline state, and the high Prandtl number, you get active turbulence. Qualitatively, we sort of capture this experimental phenomenon. Then I might ask myself a question that whether this kind of, okay, as you can see now, the Prandtl number at the beginning, it leads to, melting phase transition. At a certain point in the dense regime, you get laminar-turbulent transition. So just one parameter, right? I'm trying to think whether such a system, I can find such a phenomenon in the non-active classical fluid mechanics phenomenon. So I did not claim this non-existence in our paper, but now I think I might find it actually. If we think about a block of ice between two plates. So now I just tune the temperature of the bottom plate. Of course, if I increase the temperature, it will go from to melt to liquid and become gas. But in the meantime, I think about it. If I tune the temperature, of course, it will also undergo this classical Rayleigh-Bénard instability convection and the Rayleigh-Bénard turbulence, right? And a lot of fluid mechanics people are working on this field. So in principle, this is the temperature looks like my Prandtl number here. So I can find it. I'm lucky I did not claim this non-existence in our paper. So there's some more observation to make is about the interaction between a few particles. So in this classical paper, they found that two of these particles, they can either reflect each other, the trajectory, or crossing each other. So this is also being theoretically produced 1 year before. And in our case, what we find is that we find this trajectory, but simultaneously, we can also find this parallel swimming state. Okay, so this parallel swimming state, at the beginning we thought we never find it experimentally until very recently, 2 months ago, there's an archive paper, uploaded by an Indian group. They found this parallel swimming state. So when they are parallel swimming, we might think that because those particles, they are intrinsically repulse each other due to chemically repulsive. So there must something to counterbalance this chemical repulsion, which in fact can only be hydrodynamic attraction. So now what we do, okay, if this hydrodynamic attraction becomes strong enough or dominates this chemical repulsion, it might explain this string formation seen in the experiments as well as reproduced in our simulation. Now what we do is that we disintegrate this chemical effect and the hydrodynamic effect, but just look at the hydrodynamic attraction, we can find that indeed this hydrodynamic attraction velocity can grow with Prandtl number. And the last comment I want to make is that in fact, if we just want to look at the crystalline formation with these chemically active particles, we do not need to consider hydrodynamic interaction. And this is the work they have reproduced. So, okay, this is the end of my talk, and thank you.
Question? Yeah.
So when you interpret the change in size as a change in the Piclet number, how do you know that the other parameters don't change with size? For example, the diffusion coefficient or others?
Let me come back. Let me here. So here, I think this A and D, this thing, D, I mean, if they use the same fabrication and they use the same solvent, then I can assume that D is similar, right? Oh, sorry, A and D, these things. If,
What is M again?
M is like mobility, how the velocity depends on the chemical gradient.
M is not the Phoretic mobility of the particle, it's the mobility that you...
Yeah, you're right.
If you impose a certain gradient, how much velocity
Yeah.
you get at a surface, so the length scale that comes in there must be the interaction scale.
Yeah, so here, the only thing...
Particle scale only comes into a, little a.
Yeah, so I can only say if they use the same fabrication method, then many of these, we cannot measure that or characterize it numerically. So I can only judge in this way. Thank you.
Other questions? Can you go back to your crystalline state? The movie preferably. Okay.
Maybe I play a little bit more.
Yeah. So presumably, I mean, the dynamic structure factor of this system would actually have oscillations. Is it at a single wavelength or many, is it many wave numbers or?
But if we choose the packet number small enough, then it will become stationary.
Completely quiet,
Yeah.
is it? But
Yeah.
do you have a crystalline, do you have a sort of shaking but still crystalline state, or do you not?
In this case, we claim, but because this packet number we choose is not very far away from the threshold.
I see.
But in principle, we can, right? Of course, here what you can see, I mean, of course, there's always been numerical discretization, and we cannot get rid of. And another issue is the arbitrary periodic symmetry we impose in the simulation. Because if you originally everything should be hexagonal symmetry, then now you impose like arbitrary kind of periodic symmetry, which will also influence the dynamics with what we think.
Okay. Yeah.
In this video, I'm wondering about what kind of orientational order do you find in these states?
In which state?
In the crystal, in the Wigner crystal, for example, is there also some orientational order with the finite?
Once they become stationary, because they don't have polarity. The polarity is just from their motion. It's not like Janus particles, they have intrinsic one. But once stationary, there's absolutely no polarity at all, no head or tail, no coated, non-coated part. It just really become isotropic.
I see. And what were those arrows then on the?
Not isotropic, right? Eccentric.
Pardon?
Eccentric.
Triangular.
Arrow is still the swimming speed, but the arrow, the swimming velocity. Still the swimming velocity, which I can do, right?
Yeah.
Even the swimming velocity is super small, I can still get a unit vector.
Okay, there are no further questions. Let's thank Lailai.